There are over 1 billion cars worldwide. They are the result of massive improvements in manufacturing processes, mass production methods, and material engineering. But the pinnacle of automotive performance requires a completely different approach. These vehicles are pushed to their limits every time that they are on the track, and every second counts when it comes to beating the competition. Only the best materials are used. Cost is no object, as Grand Touring cars must run right at the limit of their performance for hours on end. These Grand Tourers are raced in 24-hour endurance races on legendary tracks. There are numerous requirements set by the FIA regarding GT car specifications. GT cars are unique in that they are race-ready versions of street cars. There are some unique requirements that other race cars don't have. According to the regulations for LMGTE cars, which is the highest performance level of Grand Tourers, Grand Touring cars must 1. Be mass-producible and street legal, although mass-producible in this case only means one car a week. 2. GTE cars must have a minimum weight of 1,245 kilograms. And finally, there are material restrictions as well. Carbon fiber, magnesium, and titanium can only be used on parts that are made of these materials in the mass-produced version of the car. Additionally, materials with a specific yield modulus higher than 40 gigapascals per gram per cubic centimeter are explicitly prohibited by these regulations unless, again, the exact same material is used in the mass-produced car. These restrictions are all incorporated into the design of these cars. Fortunately, in our hypothetical scenario, we are designing the car from the ground up, and as such we don't have any restrictions on maximum yield strength or utilization of restricted materials, because we are not limited by an existing road car's material selections. We do, however, still need to meet the mass production and street legality requirements, as well as the minimum weight requirement. GT car chassis are usually split into two different components. The cabin, also known as the tub or monocoque, acts as the base, and a crumple zone superstructure is added to this for crash protection. The crumple zones act by absorbing kinetic energy through plastic deformation, while the cabin serves the opposite purpose. It is designed to remain completely rigid, as any deformation in the section would result in the driver being crushed. Alongside these components is the roll cage, a component designed to prevent the roof from caving in on the driver in the event the vehicle flips over. To increase the responsiveness and peak performance of the car, the key factor in GT car design is weight. The energy required to reach a velocity is proportional to the mass of a vehicle, and engine output is measured in joules per second, also known as watts or horsepower, so reducing the mass improves the car's acceleration, handling, and peak velocity. Therefore, minimizing density is a goal in this process. A number of assumptions were made regarding the mechanics of the collisions that the frame must withstand. For side impacts, aka T-bone collisions, we assume that the other car will have a crumple zone that results in a retardation to zero speed in a time of approximately 0.5 seconds. We also assumed that the upper bound of survivable impact speeds with available materials is 100 km per hour. Thus, by momentum equals mass times velocity, and force times time equals mass times velocity, a force of 69,450 newtons will be transferred to the superstructure upon side impact. Additionally, it was assumed that the car will weigh as little as allowed by LME specifications, 1,245 kilograms, and that the monocoque itself will weigh a maximum of 500 kilograms. For the superstructure, our MPIs involved maximizing the ratios of yield strength and Young's modulus to the density of the material. This balances safety and performance by minimizing mass and maximizing cabin impact protection. For the roll cage, we assumed the same forces as the superstructure undergoes would be applied to it. This gives us a safety factor of approximately 3. That is, in the event of a rollover, it can support 3 times its own weight. This provides protection in the event that the car is flipped at speed, and thus hits the ground at speed, exerting a greater force than if it were merely placed on its roof. The roll cage was limited to a maximum weight of 100 kilograms, as it is only used in case of an accident, and thus is otherwise dead weight.
The MPIs of the roll cage are mostly the same as the superstructure, but the roll cages use cylindrical beams rather than oblong beams. This alters the geometric constraints slightly. The findings were very similar to that of modern GT car materials. The thickness of the monocoque and the radius of the roll cage were free variables. The cost was not a factor, as GT car manufacturers spend millions of dollars on individual cars. However, manufacturability was still an issue and was considered while selecting materials. Both the roll cage and the monocoque was allowed to deform to a maximum of 2 mm on impact to keep the driver safe. After using the Ashby plots, we chose epoxy carbon fiber, aramide fiber, and aluminium alloys. Aramide is much safer than carbon fiber as it doesn't create sharp edges upon shattering. However, it is very tough to machine and create complex structures from. Aluminium was used previously on GT cars, but was replaced by carbon fiber, as carbon fiber is over 50% stronger than aluminium. Therefore, we chose carbon fiber epoxy. The same applied for the roll cage, as the MPIs are almost the same. The crumple zone is a highly complex structure which is made in a honeycomb arrangement and uses localized buckling that propagates through it, absorbing a lot of energy of the impact due to plastic deformation. It acts like a spring in the way that the more it is compressed, the more energy it takes to compress it further.
Corrosion was not a large consideration due to the fact that GT cars do not go long periods without maintenance. Even if it is raining during a race, the car will be given a full check over as soon as the race is done and before the next race starts. In conclusion, the machinability and strength-to-weight properties of carbon fiber make it an ideal material for use in high-performance cars, as lower weight ensures better responsiveness and speed, and higher strength ensures survivability in collisions.